Boa tarde a todos. Tudo em português, and we move to English. I'm delighted for the chance from the organizers to give this speech on. It's a great opportunity, and it's a very timely manner to discuss state of the art of cancer immunotherapy. It's a rapidly evolving field at the moment, and we have had several major breakthroughs in the last few years, really. After 100 years of immunotherapy basic research, we're moving into real clinical effects. Most importantly for all of you also to realize that immunotherapy is coming out of the closet where it's been hiding with melanoma for a very long time, and it's actually now spreading to it is on its way into many other cancer types, including some of our most common ones like lung cancer. So it's really quite an exciting time for me and a lot of the industry and scientists involved in this. We have immunotherapy of cancer. So basically, there is endogenously an immune surveillance of immune effector cells that try to prevent tumor formation. Tumor finds ways to evade this by immune suppression or immune evasion, and we're then trying to use immunotherapy to shift the balance back and repress the tumor. So simply put, what we have to work with here is the immune system. It's cancer immunotherapy is comprised of various strategies to enhance or de novo generate immune responses against malignant tumors. And the central tool is the immune system. So this was basically created to fight off anything that's biologically dangerous to us. How to solve that question? What it does is really, it bases everything on recognition of self and not self. In that way, it can basically recognize anything. Its primary function is definitely fight off pathogens from an evolutionary point of view, and it's clear from animal model systems and from primary immune deficiencies. It's an extremely powerful system. You know well that misdirected in autoimmunity is a lethal disease. It's really quite powerful in both what it can do for good and for bad. It has innate, very rapid responses and adaptive components which give you immunological memory, obviously. So, although the immune system has developed primarily to patrol the body and fight infections, all tumors, yes, all tumors can be recognized by the immune system. That doesn't mean that you get an immune response against every single tumor, but they all express antigen, they all carry mutations. Basically, per definition of being a tumor cell, you will carry mutations and you will those be possible to recognize. So, and we know this from that in some cancer types, it's quite obvious that immune cells, you can isolate them and they can immediately kill the autologous tumor, such in the case in melanoma, for example, it's quite easy. You can also find antibodies against many other tumor types in the serum of patients, untreated patients. So this is naturally ongoing. There's strong correlations, moreover, between the number and types of immune cells that infiltrate a tumor and the prognosis of these patients, including overall survival. And this has been pushed now in the so-called Immunoscore by Jérôme Gallon. And basically, for example, in colorectal cancer, the Immunoscore that you get by looking at what immune cells that infiltrate the tumor actually give you better prognosis of the patient than any other marker, including normal tumor staging and so forth. So it has an enormous importance, and the interesting thing here is to remember we're looking at a resected piece of tumor which is no longer in the patient, and we're not giving any kind of immunotherapy. So even though it's not really involved in anything we do with the tumor, it still has an extremely strong prediction of what it's going to do, of how the tumor is going to do. What we usually work with in the tumor immunology is primarily CD8 T cells. They express alpha-beta T cell receptors that recognize small peptides bound to MHC class I molecules. Now, the T cell receptor is generated through somatic recombinations. So there's a huge variety of T-cell receptors, 10 to the 10 or so in each of us. And there's also a large polymorphism in the HLA molecules. And they can bind billions of different kind of peptides altogether. So you're looking at two very diverse set of molecules that are looking for a very specific interaction. And T cells, when they recognize their cognate peptide in the context of a certain HLA, they kill by perforin granzymes or death receptors such as Fas ligand, for example. And it's very clear from animal work that CD8 T cells are critical to eliminate tumors. If you have a mouse that lacks CD8 T cells, so lack MHC class 1, which means it cannot develop CD8 T cells, you're more susceptible to cancer, and you can adoptively transfer CD8 T cells and you rescue the mice from cancer. Now, all tumors are not equally immunogenic. I say that all of them can be recognized, but not all equally immunogenic. So, for example, we know that many can induce spontaneous immune response, as I mentioned. Immunodeficient mice also develop higher numbers and faster growing tumors. And this is because the immune system, the tumor is growing up in an environment of an immune system. Basically meaning that if we wipe out any part of the immune system, in this case gamma delta T cells in our lab, you see that at each point, the green measurements here representing the mice that lack a certain part of the immune system, the tumors are bigger than in the wild type mice. So the wild type mice has T cells that's constantly suppressing the growth. This is true also for many other components, in particular the interferon gamma, interferon-related signaling pathways. So basically, to illustrate this, if we take a normal mouse and an immunodeficient mice, and we use an oncogenic, and we induce a tumor, we're going to get two tumors, but they're going to be slightly different. And the one that has been educated or developed in a normal mouse will have been developed under pressure of the immune system. So if you take out this tumor here, and you inoculate that in a normal mouse, it will be able to grow because it can already withstand the immune pressure. If you were developing in the absence of an immune system, you were not sculptured to not be recognized. And therefore, if you take that tumor out and put it in a wild-type mouse, that can not grow now. So clearly, the immune system is there and constantly shaping all tumors that you face in the clinic, anything that's present clinically, basically. So this is a balance going back and forth that can either lead to eradication or tumor formation at a very early stage. So after neoplastic transformation, you get a cancer cell expansion, and at that time, you get initial elimination of some or all cancer cells. If you eliminate all of them, you're going to reach protection, and we're never going to see that cancer because it's eliminated before it presents. If not, usually what happens is you enter a stage of equilibrium. And this, you can see that in experimental system, this can actually go on for years. So you can have a constant Cold War going on, and basically they balance each other. So you can take mice that have had a tumor that has been undetectable for a year. You then eliminate the immune system, and the tumor comes right back up because it's been suppressed constantly over and over again. So either this equilibrium can go either way, of course. So after a while, either we're going to reach protection again and a dormant tumor, or the tumor is going to develop, basically select for something, some variant that can no longer be recognized. By then, you get tumor cells that are now outgrowing the immune system, and you get immune evasion and immune escape. This can also be achieved rather than becoming resistant to the actual killing, by that the tumor microenvironment fosters a very immunosuppressive environment through regulatory T cells or myeloid-derived suppressor cells, etc. So there are two different ways that the cancer can evade the immunoediting, immune recognition, and that's basically cancer escape on the top and the immunosuppression on the bottom. Interestingly, if you take the very same tumor in animal models again, and you isolate the immune cells 5 to 8 days after you inject the tumor, if you isolate those cells and study them, they are anti-tumoral. So you have cells, you know that if you take them out and study them, you can see that they are able to kill tumor. If you leave that very same tumor and instead take it out at 14 to 17 days, you will see that those cells are now pro-tumoral. So there's a shift over time in the content of a tumor, moving from the early immune recognition, immune surveillance phase to the immunosuppressive phase. Finally, the tumor antigens, they are specific to certain kind of tumor. If we induce a tumor in one organ, it's going to be different than others. That's obvious for all of you from a clinical point of view, obviously. To illustrate that, basically, a mouse can only recognize related tumors. So there are tumor antigens that are shared. So melanomas share a lot of antigens. Lung cancer share a lot of antigens between them. So within each tumor type, there is a shared pool. Basically, we can see on the bottom here, there's a tumor-associated antigens, are normal antigens expressed in these tissues, but they're overexpressed in the context of a tumor. For example, MHA3 is expressed by many melanomas and many lung cancers, HER2/neu in many breast cancer and colon cancers, etc. On top of that, you also have tumor-specific antigens, meaning now we're looking at de novo proteins, mutations in tumors that create new proteins that don't exist anywhere else. So these are the truly tumor-specific antigen. So the beautiful thing about the tumor-specific antigens is that they are potentially, there's no immune tolerance against them, so they can be very strong antigens, and they are not expressed on any normal tissue, so they should be really safe. The problem with the shared antigens is that they are shared with normal tissue, and therefore there's always a strong correlation with autoimmunity when targeting these. Now, the bad part about the tumor-specific antigens is that they are going to be unique for each patient and perhaps even each tumor. So you basically have to find the antigen for each and every individual. So it's still a huge effort. So that's really where personalized medicine will maybe change this in another 5 years or so, I would say. The tumor-associated antigens, on the other hand, they share between large parts of the patients of any given cancer type, and therefore they are much more feasible to apply. Basically, there's 4 main immunotherapies that have been pushed against cancer. Cytokine treatments that just try to reinvigorate the endogenous immunity. Antibody checkpoint blockade, basically immune cell modifiers or checkpoint blockade, such as anti-CTLA-4 or anti-PD-1 antibodies. That also basically enhance the endogenous pool of immune effector cells. Then we have where we try to evoke antigen-specific responses. We can do that through vaccines. You can vaccine with peptides or plasmid DNA or viral vectors or dendritic cells, as we heard this morning in the workshop. The problem there is if you have immune suppression, it's going to be very hard to make that efficient. On the other hand, you can also try to go antigen-specific through adoptive cell transfer, which I will describe in more detail here. So basically what you could say, cytokine treatment only really works in very immunogenic tumors, such as melanoma, which has a lot of mutated antigens. Vaccines work relatively poorly, at least in advanced disease. It may have much more of a niche in early treatment, but of course it's hard to test that setting clinically. So I'll go more into the front runners here, basically antibody-based treatments blocking immune checkpoints and adoptive cell transfer. So basically, a normal T-cell response, and a normal T-cell response is always versus a pathogen, because that's what they're there for. That's what they evolutionary have developed for. You have a huge burst, a strong activation and multiplication of T-cells. They clear out the antigen, the pathogen, and when that's done, they have to contract again. Otherwise, we'll be full of T-cells pretty fast. So you need to create that space again. You leave a surviving memory here, very small. This whole burst has to collapse down. And that's mediated naturally by engaging CTLA-4 or PD-1. So they are there to reduce the immune responses. And they should be. The problem is if a tumor expresses ligands for CTLA-4 or PD-1, then you run into the problem that the immune system, the tumor cell will actually shut down the anti-tumor immune response. There is a whole array of different inhibitory receptors and a whole array of activatory receptors on T cells that could be manipulated. And basically, CTLA-4 and PD-1 are the most dominant inhibitory receptors, and those are also the ones that have been furthest explored. I'm not going to go into detail on ipilimumab. It's already approved and finally also available for National System National Saúde, or something like that, yes. Instead, we're already looking forward to the next round of reagents now, which is really anti-PD-1 and anti-PD-L1 inhibitors, which have very promising results also outside of melanoma, so 20-30% response rate in non-small cell lung cancer and renal cell cancer. And there's a lot of different reagents in clinical trials, and it's really it's moving on all possible kind of tumor types. In models, in animal models, it turned out that a combination of anti-PD-1 and anti-CTLA-4 worked out really well. So why is that? I told you those are the two main players. And what it turns out is that when you block one of them, the cells tend to upregulate the other. So if you block CTLA-4, you will get more PD-1 expression. So they will compensate. So if you block both, you really have no way for the cells to be shut down anymore. And sure enough, in the first combination trial of nivolumab and ipilimumab in advanced melanoma, the objective response rate was 53% at the highest dose. So it's really encouraging and synergistic between the two. So that would be very interesting to see how that follows out. One important thing about these reagents are that they really set all the potentially tumor-reactive cells loose in the body. That means that both tumor-specific antigens, private antigens, and tumor-associated antigens are in play here. And by careful studies, it's actually been shown that both are probably involved in the recognition. So for example, how much immunity you have versus nucleic ESO1 here, which is a tumor-associated antigens, predict response rate and overall survival to ipilimumab treatment. So clearly tumor-associated antigens are involved. But it's also been shown that neoantigens are being driven, T cells recognizing those are being driven in ipilimumab-induced cancer regression. So both tumor-associated antigens and tumor-specific antigens seem to be important, and that opens a possibility for adoptive T cell transfer. This has basically been pioneered in hematopoietic stem cell transplantation for leukemias and autologous T cell treatment for metastatic melanoma. Briefly, the tumor-infiltrating lymphocytes, I already told you that they are very predictive of the clinical course, and so it was a reasonable step to take to use this prognostic value and try to make an immunotherapy of it through adoptively transfer the expanded cells. What you do basically, you take a tumor sample, cut it in small pieces and add a lot of IL-2. The T cells just crawl out, and then you give these back together with IL-2 to support their in vivo survival. By doing this, you get about 20% objective clinical response rate, which is actually quite good considering we're looking at stage 4 metastatic melanoma patients here. However, they realized that one key to improve this dramatically is that you can precondition the host. So if you empty the host, so to speak, by giving non-myeloablative chemotherapy, you can now boost the response of the same kind of TIL cells to 49% objective clinical response rate and complete remission in 22%, and with very long disease-free survival, so they look like they cures. Furthermore, animal models suggested the more you deplete, the better responses you will have. So by adding 12 gray of total body radiation, the last few trials now have pushed the objective response rate up to 72% in metastatic melanoma. It's mind-blowing. And you get CR in 40% of those, and they are disease-free for over 7 years now, actually. So they basically cure 40% of the patients. Now, this is an extremely aggressive treatment. You actually need to give autologous hematopoietic stem cell transplantation just to save them after the total body radiation. But it is an important proof of concept that the immune cells can really attack tumor and kill them in an extremely potent way. The problem is that melanoma is not our most common cancer, and it's most certainly not our most deadly cancer. So the real leap is to move to other tumors. And the problem is that TIL cells can easily be isolated from melanoma that are tumor reactive. It's very hard to do that from anything else. But if a T cell is guided almost solely by its TCR, if we can clone the genes for that TCR, so we find one good T cell, we clone that TCR, then we can adoptively transfer that reactivity to any cell, meaning also that we can make autologous tumor cells recognizing any specificity of our choice. Alternatively, modern molecular biology also allow us to, instead, let's even not use T cell, you can use the variable fragment of an antibody and link it to something that looks like a super TCR on the inside. This is a CD3 SADA domain plus co-stimulation. By doing that, so basically all you need now is one good T or B cell that recognize what you want. Molecularly, you can engineer this to make a TCR that you can clone or a chimeric antigen receptor, a CAR. You can express this in some kind of vector format, usually a retro or a lentiviral vector, and then you transduce patient autologous cells that now express this receptor. They will still be autologous. They will have a T cell receptor of your choice, but they will be autologous cells. So now you can generate vast numbers of highly defined tumor-reactive T cells of your choice that have the recognition motif of either TCR or even a B cell receptor, but it signals like a TCR. One of the first things people did was Herceptin is a pretty good success story in breast cancer. So they took the antigen, the binding port, the variable fragment of a Herceptin antibody, and they made a core of it. We have vast experience of treating patients with Herceptin. What we did not have vast experience of is how much more sensitive a core with this same motif is. So whereas you don't see any significant binding of Herceptin in the lung, what happened is that this patient went through massive cytokine storm because there are very small amounts in the lung that these very sensitive cells can recognize. So it's extremely potent. What has been a big success is really to find the safe antigen. So basically you have to define something that is expressed on all tumor, but that you basically can live without on the normal tissue. So if you wipe the normal tissue, you have to be okay. B cells, we don't really need this, right? So you can live on IgG, all supplementation. So there's about 40 clinical trials testing CARs today. And most of them are targeted versus CD19. And they are extremely efficient in both BCLL and BALL. You also generally wipe out all your normal B cells, so you lose your antibody production. And there are ways to get around that, of course. In the follow-up studies, you can put in suicidal genes. So after you killed off the tumor, you can shut down the response. But the TCR and CAR engineered T cells, they're generally applicable and circumvent the whole need to now find tumor-reactive T cell of anyone. We just need normal blood, PBMC, and a receptor of our choice. And that can come out of a very unusual, successful patient. It can come out of a transgenic mouse. It can come out of, you can basically build whatever you want. The only problem is, of course, until you put it in vivo, you don't really know how it's going to behave. Like in the case of Herceptin, you expected that you knew how that would bind, and actually it turned out it had a different recognition pattern than expected. We can grow this in clinical scale. We can make billion of these cells quite readily. And you can achieve substantial and sustained objective clinical responses. There is a risk of off-target toxicity, on and off-target toxicity, and the price is still about $15,000 per patient, even in an academic setting, without that anyone makes any profit. So it's an expensive therapy, but so is, of course, hematopoietic stem cell transplantation that we do 50,000 a year in the world. So there are some things that need to be streamlined, but we're definitely moving towards an applicable point of this, not in every small hospital in the countryside of Portugal, but definitely on more bigger medical centers. And so I would say, looking at what the future holds and the current challenges. So one problem here is that you target something with a very high defined specificity. So you're really hitting one target, in this case CD19. So actually, even in the first couple of trials on BCLL and in BALL, both cases, about 1 in 20 patients relapsed with a CD19 negative tumor. Basically, no, you don't hear about CD19 negative tumor because they're not there, because the pressure is not usually there. If you put enough pressure, you will basically drive selection of anything that can survive that specific pressure. The solution to this is that people now do multiple CARs, CD19, CD20, CD22, CD23 are all in ongoing clinical trials. The costs, how do we solve that? Well, one way is to try to mass produce this in a central facility, and people have taken it further. They actually use zinc fingers to wipe out the HLA gene, so that you now have allogeneic cells which don't express HLA. Therefore, they can no longer be recognized by T cells as allogeneic, and they can persist. NK cells should kill them, so then you just overexpress a non-classical MHC class 1 molecule such as HLA-G. So then we're actually moving towards an off-the-shelf cellular product which you could use on any patient, getting around the whole personalized medicine, which of course dramatically can change the price of these. You have to be wary about the safety of new receptors, but what you can do and what has been done recently now is that you use logic gating. Basically, you put in 2 receptors, and you require that A and B has to bind for you to get signal, or you do that if A binds, it doesn't matter if B binds. It's an overriding negative signal, so that can also be achieved. The next level, of course, once we solved what to target, is now you worry about whether your cells traffic to the right spot, etc. And that you can also engineer on top of all this, because you can just add chemokine receptors and so forth. It's already been done in the preclinical setting, and significantly enhance recognition in animal models and so forth. So you can basically make them resistant to oxidative stress, and you can make them traffic to a certain site, CXCF4 for the bone marrow, or you can basically design these very detailedly. And finally, there's the expectation. Immunotherapies often give a relatively low response rate, but very long-lasting responses, whereas targeted therapies often give frequent response, but much more short-lived. And the idea was that the combinations may really boost each other. And sometimes they will, and sometimes they won't. So, for example, I told you the combination of ipilimumab and anti-PD-1 antibodies is extremely promising, very synergistic, whereas it did not turn out that well to combine ipilimumab with BRAF inhibitors. And the reason is that even though they both have limited toxicity, when you try to combine them, you run into a liver toxicity that actually limits your results. Obrigado.